So let's go ahead and talk about the setup of the hypothesis testing. So we can see that the test statistic for the goodness of fit test is a chi-square test statistic, similar to the t-test statistic. And essentially what it's taking is each observation and subtracting the expected count. And basically they're finding that difference between the error, right, between the observed and the expected. They're squaring it and dividing by the expected count. And then for each category. And then they're going to add all that up. So once again, there's the k minus 1 degrees of freedom, but there are criteria, just like with the prior hypothesis testing, we always have like two criteria, right? In this case, we have two criteria, but in this case, it will be all expected frequencies are greater than or equal to 1, and no more than 20% of the expected frequencies are less than 5. So once we calculate the expected counts, they should not be less than 5, no more than 20% of them. So we'll go ahead and do that in the next example. So just like anything else, here is the goodness of fit that the same 5 steps as usual. Step 1, do your hypothesis. Step 2, level of significance, draw the curve. Step 3, make sure we calculate the expected counts, which we just did in the previous example, right? And we'll make sure that we'll verify the two requirements that we just discussed, and then we'll compute the test statistic. Now, don't worry too much about the test statistic because we can do that in the calculator. The calculator will give us that. The p-value approach, we'll go ahead and use the calculator for the goodness of fit test, GOF, right? And then same process. If the p-value is less than alpha or greater than alpha, we reject or not reject. And then the conclusion, and we just interpret in terms of the claim. Okay, so we have a goodness of fit test. So if you go ahead and go to stat and test and goodness of fit test. Now, the first thing you'll have to do is put in the observed counts from a sample and then the expected counts, and then we'll go ahead and conduct the test. So if we go to the calculator, all right, and go to stat and go to test, and hit up, you'll see all these other tests we haven't touched. As promised, we're using all of them. Notice D is chi-squared GOF test. So go ahead and highlight D and hit enter. So you can see it already knows what it's doing. You need the observed and the expected. And then put the degrees of freedom, which is the number of categories minus 1. And go ahead and calculate or draw it however you want to do it. So don't forget that the degrees of freedom is just the number of categories minus 1. Okay, so if you don't see this test on your calculator, here is a way to find the test statistic so you can find the p-value. I encourage you to use the current calculator. If not, you can try to download that TI Smart View, which will have it, but also some online calculators have it. Okay, so continuing with that same example with the sociologist and grandparents caregiving for their grandchildren for a certain number of years, there was a sample taken from that 1,000 caregiving grandparents, right? And because we had certain percentages, these were the same expected counts we just calculated, right? But when they took that sample, here are the ones, the observed ones. Here are there was actually in the 1,000-person grandparent sample, 252 of them were caregiving to their grandchildren for less than a year. We expected 228. So there is some difference between what is observed in our sample when we do the survey versus what we expect. What the goodness of fit test will do is say, well, even though they're a little off between what we actually observed from our sample to what we expected, is it still a good fit? Are these percentages still pretty good to use? And so because that's a claim, right, we're kind of saying, is it or isn't it? We're able to test that by hypothesis testing and see if it's a good fit. Okay, so we're going to test the claim that the distribution is different today than it was in 2000 at the zero point zero 0.05 level of significance. The first thing we want to do is set up the hypothesis. So in this case, we're going to actually, there's no parameter, like it's not a quantitative data, so we don't have a parameter to write in. We're going to have to use a complete sentence. So essentially, the null hypothesis is status quo, right? Nothing's changed. So we'll just say the distribution from the census in the year 2000 was uh, was a good fit, right? So it's not different today, right? So we'll just say that the distribution for caregiving grandparents is the same today as it was in 2000. And the null would be that the distribution and then different today. Okay. Step 2 is identifying the alpha, and they gave us the alpha to be 0.05. So step 3 says that we need to calculate the expected counts. So 1I was to calculate expected counts, but we did that in the previous example, right? So that's these. Let me go ahead and highlight that. The second part is meeting that two criteria, right? So actually this is A and this is B. So 1I in the criteria was that if we scroll back up, we can see that A has to be the expected counts, which we were given, and then B is verify the requirements. So we need to make sure that all expected counts are greater than or equal to 1, and that no more than 20% of expected counts are less than 5. So let's go ahead and make sure those two are satisfied. So any category has to be greater than or equal to 1. And we can see that every expected count is much bigger than 1. There are hundreds, right? So that's done. The second criteria says that no more than 20% of the expected counts can be less than 5. Well, none of them are less than 5, so we're okay there too. So most likely they're always met. And C is we're going to go ahead and calculate the chi-square test statistic, and we're going to do that in the calculator. And so let's go ahead and move on to step 4, which is finding the p-value. So let's go ahead and once again, we're going to go to the calculator and hit chi-squared Goff test. And the first thing we have to do is put in list 1 the observed, and in list 2 put the expected. And then we can calculate it. So let's go ahead and do that. Let's go to the calculator and go to Stat and go to Edit. And we can go ahead and clear our list. Okay, so in list 1, we're going to put the observed, which is 252, 255, 162, 331. And then in list 2, we'll put the expected counts, 228, 239, 176, 357. And now let's go ahead and go to that stat test in D. Okay, my observed I put in list 1, my expected is in list 2, and the degrees of freedom is the number of categories minus 1, and recall that that was 3. Okay, so the first thing we could do is draw it. And we can see that it's skewed right. And it gives us the test statistic and the p-value. So let me drag this over. Okay, so the test statistic would be 6.6046, and the p-value is equal to 0.0856, and our alpha was 0.05. So when we compare the p-value with the alpha, we can see that the p-value is larger, and so that means if we took another random sample of 1,000 caregiving grandparents, that the probability would be larger than to get the same results would be larger than making a type 1 error, and that means that there's just not enough evidence to support any change, right? So here we do not reject the null. Okay, and just to kind of give you an idea, this test statistic, that's what this chi-square is. Okay, and we can put the degrees of freedom here, right? So here, let's put a note here. So the degrees of freedom would be the number of categories minus 1, which is 3, and that's what we used inside our test. Okay, so that's kind of the process. So first you would set up the hypothesis test, determine the alpha, and then go ahead and make sure to calculate expected counts if you don't have it already, and then make sure the 2 criteria are met within step 3. And then we can calculate the chi-squared and the p-value and the graph all together in the calculator. So it's super, super simple and fast. And now we can go ahead and interpret, right? So step 5 would be that there is not enough evidence to support the claim that the distribution is different today.